Welcome back to the Deep Dive. Today we're diving really deep into something that's fundamentally changing how we customize and interact with powerful AI. We're talking about the world of large language model fine-tuning. If you ever wondered how these massive, general purpose AIs get turned into specialized experts, or maybe how you could adapt them for your own unique needs, well, this deep dive is definitely for you. Our focus today is squarely on LLaMA Factory. It's this open source framework that's honestly a bit of a game changer. It makes a previously really complex process incredibly accessible. So our mission today, let's peel back the layers, understand the technical how and why, explore the implications, and really uncover the ingenuity behind this tech. And we'll do it all in a way that's hopefully digestible and insightful for you.
That's absolutely right. Yeah, we've got a pretty comprehensive journey mapped out. We'll kick things off by really establishing why fine-tuning isn't just, a nice-to-have feature. It's actually a critical step for maximizing the utility, unlocking the true potential of these large language models. Then we'll get into the real core of our discussion. LLaMA Factory itself will meticulously explore its remarkable technical features, the things that streamline and really democratize the fine-tuning process, making it surprisingly efficient. And finally, we'll ground our understanding in real-world performance. We'll look at implications, draw insights from recent benchmarks, and examine the role high-performance hardware plays in all this. This deep dive, it's really about equipping you with an understanding of the technical underpinnings, the nuts and bolts, and the practical applications of adapting these powerful AI systems. We're focusing on what it means for tactical decisions out there in the field.
Okay, let's unpack this right from the very top then. Why do we even need to fine-tune these massive LLMs? I mean, aren't they already incredibly smart? They're trained on, like, the entire internet, practically all human knowledge. Shouldn't that be enough?
It's a perfectly natural question, and it really gets to the heart of why specialized adaptation is so crucial. Think about those general-purpose LLMs, the ones trained on truly immense and diverse data sets. They're kind of like brilliant generalists. They can hold a conversation on almost any topic, answer a huge range of questions, generate creative text, summarize articles across, well, countless domains. Their breadth of knowledge is frankly astounding. But much like, say, a general practitioner versus a specialized heart surgeon, they inherently lack that deep domain-specific nuance.
Okay, so they're good at a lot of things, but not necessarily expert at any one specific thing. It's that depth versus breadth idea.
Precisely. While they perform adequately in many areas, they can struggle significantly when they're confronted with industry-specific language or highly technical jargon or complex conceptual frameworks unique to a particular field. Imagine asking a general LLM to draft a complex legal brief, or diagnose a really nuanced medical condition, or provide a precise financial analysis using very specific market terminology. They might give you something back that sounds plausible, but when you look closer, it often lacks the precision, the contextual appropriateness, or even the factual accuracy required for serious professional applications. And that's where you run into the notorious hallucinations, where the model basically fabricates information that looks convincing but is actually entirely incorrect for that specialized domain.
Ah, yes, the dreaded hallucination. So it's not just about getting a slightly off answer. It could be completely made up. So it's really about achieving that deep accuracy and context-specific relevance. But is there more to it? Like a practical benefit in terms of efficiency or even cost? Does fine-tuning make a difference there too?
Absolutely. That's a critical technical and economic implication, especially for businesses using these models. When you're working with a general model for these domain-specific tasks, you often find yourself needing to craft much longer, more elaborate, really descriptive prompts. You're constantly trying to provide enough context and examples right there in the prompt itself just to nudge the model towards the desired accurate output. This whole prompt engineering overhead, I mean, while it works to some degree, it drives up inference costs considerably, especially if you're using API-based LLM services where you typically pay per input token and per output token.
All right, so more tokens in, more tokens out just means more money spent. Fine-tuning helps trim that fat, essentially.
Exactly. Now, let's talk about the tangible benefits you get from fine-tuning. Firstly, and maybe most importantly, you achieve significantly improved performance on those domain-specific tasks. By training or adapting the LLM on your proprietary data, or maybe confidential datasets, think your company's entire internal knowledge base, or a highly specialized dataset like the Docker natural language commands we'll use as an example later, the fine-tuned LLM actually learns the unique language, the specific syntax, the intricate concepts of that particular field.
So it's not just about what the model knows in general anymore, but how it applies that knowledge within a very precise, tailored framework. It really becomes a specialist.
Correct. And this process dramatically reduces the likelihood of those factual inaccuracies or irrelevant outputs, those hallucinations we were just talking about.
Hmm.
It makes the models far more reliable, more trustworthy for professional, even mission-critical applications. It ensures a high degree of alignment with your very specific technical requirements. Secondly, and as you rightly pointed out, you see optimized efficiency and often substantial cost reduction. Fine-tuned models become incredibly adept, really focused on their specific task. This means they generally require far fewer input tokens to generate accurate, relevant, and concise responses. Your prompts can be much shorter, much simpler.
Okay.
And that directly translates to lower inference costs when you're using hosted LLM services. They also tend to exhibit enhanced learning capabilities. They get better at zero-shot and few-shot learning, but specifically within their specialized domain. This means they can often perform well even with minimal or maybe even no new examples given in the prompt, further enhancing their practical utility and reducing the need for extensive in-context learning through elaborate prompting.
Wow, okay. That's a huge win for practical, real-world deployment, especially for businesses, isn't it?
Yeah.
It's really about making these models smarter, more reliable, and significantly more cost-effective for those niche applications. It sounds like it truly maximizes their potential, turning a general tool into a precision instrument. Okay, so here's where it gets really interesting for me. We're talking about training and adapting these enormous models, right? Sometimes with billions and billions of parameters. How does LLaMA Factory fit into this picture? How does it make something that sounds incredibly complex, incredibly resource-intensive, genuinely accessible to a broader audience?
Right. LLaMA Factory is, well, at its heart, it's an open source framework. And it's specifically engineered to simplify the entire process of training and fine-tuning these large language models. Its profound appeal, I think, lies in making LLM fine-tuning both easy and efficient for a remarkably broad audience. You genuinely don't need to be a deep expert in low-level AI coding. You don't need a PhD in machine learning to use it effectively, provided, of course, you have access to the necessary compute power. That's still a factor.
Yeah. So even if you're not, say, an AI researcher or a seasoned ML engineer, you could potentially jump in and fine-tune your own LLMs. That seems like quite a claim for such cutting-edge tech.
It is, yeah. And its accessibility is largely down to its low-code or even no-code approach, particularly through its integrated web UI. This user interface, it's built using Gradio, which is a great library that lets users interact with complex machine learning processes directly in a web browser. It essentially abstracts away a lot of the underlying complexity. It lets you select models, configure parameters, monitor training progress just with clicks and simple text inputs rather than, writing extensive Python scripts. And all credit for this really innovative and empowering platform goes to its creator, Hyuga.
That truly sounds like it's democratizing access to some seriously powerful technology. So what are some of its key features then? What makes it such a versatile and comprehensive toolkit?
LLaMA Factory's versatility is genuinely impressive. Firstly, it boasts extensive model support. It supports over 50 large language models that covers a huge range of popular and cutting-edge architectures. You've got staples like the LLaMA series, multimodal models like Lava, popular conversational ones like Mistral, for instance, the very efficient Mistral 7B chat, and also Mistral Moe, Quen, Yi, Gemma, Baishuan, ChatGLM, Phi. The list goes on. This broad selection means you can choose the best base model that really aligns with your specific needs, the nature of your data, and importantly, your available computational resources.
Wow, that is a huge range. Lots of flexibility there, so you're not locked into one particular model family. What about the actual training process itself? Are there different ways to fine-tune or maybe different goals you can optimize for?
Absolutely. LLaMA Factory supports a really diverse array of training stages and trainers. It goes far beyond just basic fine-tuning. It handles fundamental tasks like incremental pre-training, where you just continue training a base model on new data, and supervised fine-tuning, SFT, which is very common. That includes multimodal SFT for models handling text and images. But for more advanced model alignment, which is all about making the model's outputs more helpful, harmless, honest, it supports reward model training, PPO, proximal policy optimization, DPO, direct preference optimization, and also KTO and or RPO training. Now, SFT is the most common method, and it's what was used in the tutorial example we'll walk through. But things like DTO, KTO, or RPO, they represent significant, really cutting-edge advancements in aligning models with human preferences, often without the complexity of traditional reinforcement learning setups.
Okay, that's a lot of techniques, covering the full spectrum from basic adaptation to advanced alignment. And compute precision, that sounds incredibly important for practical use, especially dealing with different hardware setups, right? It affects what models you can even run.
Critical, yes, absolutely critical. LLaMA Factory offers flexible computation precision, which is a massive advantage for users with different hardware capabilities. It supports full 16-bit parameter fine-tuning for maximum precision if you have the high-end compute power needed for that. But crucially, it also supports highly parameter-efficient methods like frozen fine-tuning, where only a small part of the model gets updated, and LoRa, low-rank adaptation, which we'll definitely dig into more. And even more remarkably, it enables 2, 3, 4, 5, 6, or even 8-bit QLoRa fine-tuning. This relies on various sophisticated quantization techniques, things like AQLM, AWQ, GPTQ, LLM.entite, ENTI, HQQ, EOTQ.
Okay, hold on. What's the big technical implication of having so many options for precision? Why is that such a game changer for someone just trying to fine-tune an LLM?
The technical implication is huge. It dramatically reduces the memory footprint required for fine-tuning. By quantizing the model weights to fewer bits, say going from 16-bit down to 4-bit, you're effectively compressing the model's size in memory. A lot. This flexibility lets users strike a really delicate balance between precision, memory usage, and computational speed, all based on their available hardware. What this really means in practice is that it makes it possible to fine-tune much larger models on, say, consumer-grade GPUs or cloud instances that might otherwise simply not have enough VRAM. It truly democratizes access to these powerful LLMs, moving them beyond just organizations with massive data centers.
Got it. So it's about doing more with significantly less hardware-wise, making these powerful models accessible to a much wider audience. Are there also specialized optimization algorithms built in? Things to make the training process itself faster or maybe more stable?
Yes, absolutely. LLaMA Factory integrates a whole suite of advanced optimization algorithms. These are designed to enhance training stability, efficiency, and ultimately the final model performance. This includes methods like Galore, Batum, Dora, Long LoRa, LLaMA Pro, mixture of depths, LoRa plus Thra, LoftQ, PISA, quite a few cutting-edge techniques. Each of these tackles different aspects of the training process. They might aim to improve how quickly the model converges, or reduce the overall training time, or perhaps enhance the quality and capabilities of the final adapted model. For example, some of these focus specifically on optimizing the LoRa training itself, finding more efficient ways to update those small matrices we'll talk about.
And for just raw computational speed, beyond the algorithms, what does it offer? Any hardware acceleration tricks?
Oh yes. For raw speed, it incorporates cutting-edge hardware acceleration operators, specifically mentioning flash attention to and unsloth. Now, these aren't just generic speedups. They are highly optimized implementations designed to specifically accelerate the most computationally intensive parts of LLMs. Flash attention to, for example, focuses on the attention mechanism. That's a major bottleneck in transformer architectures, computation-wise. By optimizing memory access patterns during attention calculation, it leads to significant speedups and lower memory usage for those critical operations, resulting in much faster overall training times.
That's seriously impressive.
Yeah.
It really sounds like they've scrutinized every aspect of the fine-tuning pipeline for efficiency gains. Okay, one last thing on features. Once you actually kick off a training run, how do you keep an eye on things? How do you track progress and make sure everything's going smoothly?
Right. For monitoring experiments, LLaMA Factory is exceptionally well equipped. It supports LLaMA Board, which is its own dedicated graphical user interface, a GUI for real-time monitoring of training progress. Pretty neat. Additionally, it integrates seamlessly with a suite of popular external monitoring tools like TensorBoard, Wanbi, which is weights and biases, MLflow, and SwanLab. These provide really comprehensive tools for tracking and visualizing training progress. You can plot loss curves over time, monitor various other metrics, log your experiments. This is absolutely crucial for understanding how your model is actually learning, identifying potential issues early, and making informed adjustments to your training process.
Okay, so it's not just about making the process easy to start, but also making it easy to manage, analyze, and optimize along the way. It really sounds like a comprehensive end-to-end toolkit for fine-tuning. Okay, yeah. So that's the impressive high-level overview. Now, what does this all mean for you, the listener, if you actually want to roll up your sleeves and use LLaMA Factory? Let's walk through the actual steps. How do you get started? How do you practically fine-tune a model with this thing?
All right, let's break it down into a practical step-by-step workflow. Imagine you're setting this up on your own machine or maybe a cloud instance right now. A, setting up the environment. The very first foundational step is to clone the LLaMA Factory repository from GitHub. You run that command, typically git clone repository URL, and it pulls down all the necessary scripts, configuration files, all the components you'll need. Once you have the repository locally, you just navigate into that directory using your command line, your terminal.
Okay, simple enough. And then it's about getting all the right software libraries and tools installed, the dependencies, to make sure everything actually works together right.
Exactly. The next step is installing the required Python packages. Usually you do this using pip install -r requirements.txt. This command goes through a list and pulls in several critical dependencies. These include transformers, that's essential for interacting with the LLM models themselves, PEFT, which stands for Parameter Efficient Fine-Tuning, and that's crucial for implementing techniques like LoRa, and Bixham bytes. This one is absolutely critical if you plan on leveraging 4-bit quantization, as it handles the low-level high-performance operations for that. You'll also need things like accelerate and troll haul for various aspects of distributed training, and maybe some reinforcement learning pipelines.
I've definitely heard that CUDA and PyTorch compatibility can be a real headache sometimes. It seems like one of the trickiest parts of setting up almost any deep learning environment. Is that something to watch out for here too?
Yeah. You've absolutely hit on a common pain point for many folks. Yes, it is incredibly important to install a PyTorch version. Maybe something like PyTorch 2.4.0 is often recommended, but check the LLaMA Factory docs that is fully compatible with your specific NVIDIA CUDA toolkit version installed on your system. Misalignment here is a very, very frequent source of cryptic errors that can be quite tricky and time-consuming to debug, so pay close attention to that. Additionally, NCCL, the NVIDIA Collective Communications Library, is essential if you're planning on doing multi-GPU training. It facilitates high-performance communication between GPUs, ensuring seamless data transfer when you scale things up.
Good tip. And where can you actually run this whole setup? Are you confined to powerful local machines, or can you use cloud resources? What about if you're dealing with sensitive or private data?
Not confined at all, really. The framework offers significant deployment flexibility. You can absolutely set it up locally on your own infrastructure. That could be your powerful desktop with a couple of GPUs, or maybe an on-premise server cluster if you have access to one. Alternatively, and very commonly, you can deploy it within a public cloud environment. Think AWS SageMaker, Google Colab, or maybe those specialized GPU cloud platforms like RunPod or Lambda Labs. This flexibility is particularly valuable if you are handling proprietary or highly confidential data sets, as it lets you maintain full control over your data within your chosen secure environment.
Okay, great. So environment setup, dependencies installed, ready to go. The next crucial step is data, right? As we discussed, data is the foundation of fine-tuning. How do you actually prepare your data for LLaMA Factory?
Absolutely. Data prep is foundational. LLaMA Factory is quite versatile in its supported data sources. You can ingest data sets directly from popular hubs like Hugging Face Hub, ModelScope, Modelers Hub, or you can just load them from your local storage if you have the files there. Now, when it comes to the primary dataset formats, it mainly supports two key structures, each designed for slightly different conversational nuances. The first is the alpaca format. This one's widely used, very well suited for supervised fine-tuning, especially for single-turn instructions or simple Q&A. In this format, your dataset typically needs columns like instruction, input, output, sometimes system and history too. The instruction column holds the main directive. The input might provide additional context or examples. These two often combine to form the human prompt the model sees. The output column naturally contains the expected, ideal response from the model. And the history column, if used, stores a list of previous prompt response pairs, which is crucial for training models to maintain coherence in multi-turn conversations. The second main format is the shared GPT format. This one's a bit more complex, a bit more flexible. It's designed to support richer, multi-role conversations and potentially more advanced functionalities like tool use. It can include roles beyond just human and model, like human GPT for the model's response, maybe observation for external info or tool outputs, and even function for function calls. Conversations here are structured as a list of objects, and there's a specific ordering required. Human and observation entries need to be in odd positions, GPT or function in even positions, to maintain that structured flow.
That's clear. Okay, so what if I have my own custom data set, like that Docker natural language commands data set you mentioned earlier from Hugging Face? And let's say it's not perfectly in Alpaca or shared GPT format right out of the box. How do I integrate that? Do I need to manually convert the whole thing?
Good question. You don't necessarily need to manually convert the entire dataset structure, but you do need to map your data to LLaMA Factory's expected formats. For our Docker example, which comes from Matt Colty on Hugging Face, you typically create a new entry in a specific configuration file called dataseatinfo.json within your LLaMA Factory setup. In this JSON file, you reference your dataset, maybe by its Hugging Face hub URL if it's public, or just a local path if you have it downloaded. Then, the critical part, you provide a mapping. You tell LLaMA Factory which columns in your dataset correspond to its expected keys. So if your Docker dataset has columns named, say, command instruction and generated output, you'd map command instruction to maybe prompt or instruction, and generated output to response or output in the JSON config. This standardization step allows the framework to process diverse datasets as long as you provide that correct explicit mapping.
Oh, that makes perfect sense. It's about telling the system how your custom data fits into its established structure.
Okay, so data's prepared, it's mapped. How do we actually configure the fine-tuning process itself? Is it all complex command line code, or is there that friendly Weeb UI you mentioned earlier?
This is really where LLaMA Factory's no-code or low-code appeal shines and makes it so accessible. While you absolutely can define all your configurations in YAML files, which is great for command line training, automation, or complex distributed setups, the Web UI setup is often a game changer for interactive use and getting started. To get the Web UI running, there's usually a crucial initial step. You might need to modify a specific line in one of the Python scripts, often src-train-web.py, to set share true. This simple change, once you run that script, generates a Gradio link. And that link makes the user interface accessible directly in your web browser.
Okay, so you just run the script, get a link, open it in your browser, and then you're presented with a graphical interface to select options and tweak parameters. Precisely. Once you're in the Web UI, the whole process becomes incredibly intuitive. First, you'll do your model selection. You choose the base model you want to fine-tune from a drop-down list, like Mistral 7B Chat for our example. This choice is vital, obviously, as it impacts compute requirements and the capabilities you start with. Next, you select your fine-tuning method. For efficiency and accessibility, especially on more modest hardware, LoRa, low-rank adaptation, is a very common and highly recommended choice. As we discussed, LoRa is that parameter-efficient technique. It significantly reduces the number of trainable parameters, making fine-tuning much more feasible on hardware with limited VRAM.
Right. And the quantization we talked about earlier, loading the model in 4-bit precision to save all that memory, how is that set up within the UI? Is it complicated?
Nope, that's another key setting that's usually just a simple selection or a click away in the UI. You'd find the quantization bit parameter probably in an advanced or model section, and you just set it to 4. This tells LLaMA Factory to load the base model using 4-bit precision, leveraging the QLoRa technique and that bits-and-bytes library we mentioned. This is a monumental memory saver. It drastically reduces VRAM usage, allowing significantly larger models that might otherwise only fit on professional-grade, very expensive GPUs to be fine-tuned effectively on more accessible, even consumer-grade GPUs with less VRAM.
Got it. So it's really about getting a powerful model to fit within whatever hardware constraints you might have. What about the actual training parameters themselves? Things like, how intensely the model learns or how many times it sees the data during training. Yeah.
Those are your hyperparameters, yes, and they're typically adjusted directly within dedicated sections of the Web UI. You'll tune critical parameters like cutoff length. That defines the maximum sequence length the model will process during training. A longer cutoff length means the model can handle more context, but remember, it also directly increases memory consumption, so trade-off. The learning rate is another really critical one. It controls the step size during optimization, how much the model adjusts its weights each time. It's typically a small value, maybe something like 2e4, but finding the right one often requires a bit of experimentation. Compute type is also vital to get right. You should select BF16, bfloat16 if you're using modern NVIDIA GPUs like A800s or A400s, or use FP16 float16 for slightly older GPUs like V100s. Using the wrong one can lead to errors or suboptimal performance. You'll also specify things like max samples, that's the total number of examples from your dataset you want to train on. Maybe you don't use the whole dataset initially. Epochs, that indicates how many full passes over the selected data the model will make. Often just 1.0 or slightly more for an initial fine-tune is enough. Per device train batch size, that's the number of samples processed per GPU simultaneously within a single training step. A larger batch size can speed things up but uses more memory. Maybe a value like 16 is a starting point. And maximum gradient normalization, that's a technique used to stabilize training, preventing gradients from exploding and causing instability. Usually a default value works well here.
Okay. And the LoRa rank, you mentioned earlier, it had that interesting sort of inverse relationship with
the base model size. How do you set that in the UI? And what's the thinking there again?
Right, the low rank. This parameter sets the rank or dimension of those low rank matrices that LoRa injects into the model. It's adjustable in the UI, usually under the LoRa specific settings. And yes, the nuance is important for getting optimal results. While a lower rank saves more memory and parameters, the counterintuitive part is that for smaller base models, a higher lower rank might actually be necessary. Think of it this way. A smaller base model has less inherent capacity to begin with. By giving it a higher lower rank, you're essentially giving those specialized adapter modules a bit more room or depth to learn. This allows them to better capture and learn the specific nuances of your dataset, potentially compensating for the base model's smaller capacity and achieving better overall performance. It's a key design choice that impacts how deeply the model adapts to your task. And just remember, for automated workflows or distributed training across many GPUs, all these configurations can also be defined very precisely in a config.yml file. Then you'd use the LLaMA Factory ClayRyan command, often incorporating deep speed configurations for highly efficient multi-GPU setups.
Okay, crystal clear. So configurations are all set, either in the SlickWeb UI or the YAML file. How do you actually kick off the training process? And critically, how do you know if it's actually working? How do you know if the model is learning effectively?
All right, to initiate training, you'll execute a command, typically from your terminal or command prompt. If you're using a single GPU, it might look something like qdivisible devices 0bio python src train web.py. That qdivisible devices 0 part explicitly tells the system which GPU to use, GPU number 0 in this case. If you're using a configuration file, it would likely be something simpler like LLaMA factory-clanconfig.yml. Now, when you run this command, the very first thing that usually happens is the base model weights get downloaded. If you don't already have them cached locally, they'll be pulled from Hugging Face Hub. These can be quite substantial files. For instance, Mistral 7B chat is around 9.94 GRB. So this initial download might take a few minutes depending on your internet speed.
Okay, so a potentially significant initial download, but then what happens with monitoring? How do you actually see the training happening in action?
For monitoring, that LLaMA board web UI we mentioned is incredibly helpful. It provides a real-time loss graph. It typically displays both the original, maybe slightly noisy loss values from each step, and also a smooth loss curve, which helps you see the overall trend much more clearly. Simultaneously, you'll usually see verbose output streaming in your terminal or the notebook where you launch the process. This shows critical information like the current learning rate being used, the step number you're on, and the actual loss value calculated for each training step. Interpreting the loss is pretty straightforward, thankfully. A consistently decreasing loss curve is what you want to see.
Okay.
It indicates that the model is learning effectively from your data. It means the model is getting better at predicting the desired outputs based on the inputs, and it's generalizing well to the patterns in your specific data set. That's a very good sign that your fine-tuning is progressing as expected. While LLaMA Factory does offer more detailed evaluation metrics that you can configure and run periodically, the primary real-time visual feedback to gauge initial success is definitely that smoothly decreasing loss curve.
All right, so watch the loss go down. And after the training process finishes, what do you actually get out of it? What are the artifacts? And how do you use this newly specialized model for your specific task, like the Docker example?
Great question. Upon completion of the training run, the key outputs are the fine-tuned LoRa adapters. These are saved in your designated output directory. These are typically small, really crucial files specifically. You'll often see adapterconfig.json and adaptermodel.safetensors. These files contain all the learned adaptations, all the changes the model made during fine-tuning, and importantly, they are much smaller than the original base model weights, making them incredibly easy to store, share, and deploy. Now, to put your fine-tuned model to use, if you're using the LLaMA board web UI, you can often simply refresh the adapters drop-down menu. Your newly trained adapter should appear there in the list. You select it and then click a button to load the fine-tuned model, which means loading the base model plus applying your trained adapter on top. Once loaded, you can immediately start interacting with your specialized model right there in the chat interface. For our Docker example, you could then ask it questions directly like, how do I delete a Docker container named test? Or maybe list all containers and show their status.
Ah, okay. And the goal then, the proof that it worked, is for it to give you the correct specialized output perfectly tailored to that Docker command domain.
Exactly. The key is to validate the responses. You observe that the model now generates correct domain-specific outputs. For instance, it should give you accurate Docker commands like docker arm isf container name for deleting a specific container, or maybe docker apices a filter status exited for listing containers that have stopped. Seeing this kind of precise and relevant output confirms the success of your fine-tuning effort. And beyond just testing it in the UI, LLaMA Factory also provides comprehensive options to export and share your fine-tuned model. You can specify things like the quantization bits you want for the final exported model, maybe set a maximum size limit, or you can even push it directly to the Hugging Face Hub with a few clicks or commands, making it incredibly easy to deploy in other applications, integrate into larger systems, or share with your team or even the broader community. It really closes the loop from setting up your environment all the way to deploying a specialized, high-performing LLM.
That's a fantastic, really clear step-by-step overview of the workflow. And it absolutely highlights how LLaMA Factory simplifies what honestly used to be an incredibly daunting task, accessible only to a few. But for a learner, maybe someone listening right now who wants to go deeper, someone who wants to understand not just how to use it, but what's actually happening under the hood. What are some of those advanced techniques you mentioned earlier, like LoRa and quantization, and why are they so impactful for the efficiency and the capability of the final fine-tuned model?
Excellent question. Yeah, understanding the underlying mechanisms truly solidifies your grasp of fine-tuning. It lets you make much more informed decisions about your approach, how you set things up. Let's definitely delve into some of those core techniques. A. Fine-tuning techniques explained. First, we have supervised fine-tuning, or SFT. This is probably the most intuitive and straightforward method. In SFT, the model learns directly from input-output pairs that you provide in your dataset. It's conceptually like teaching a student by showing them lots and lots of correct examples. Here's the question. Here's the perfect answer. The model adjusts its internal parameters, its weights, to minimize the difference between its own generated output and the desired target output that you provided in the training data. It's essentially pattern recognition and direct imitation learning based on that explicit supervision.
Okay, so it's basically teaching by example, and the model tries its best to mimic those examples as closely as possible. Simple enough.
Yes, exactly, within that supervised learning paradigm. Now, next up, and incredibly impactful for efficiency, is low-rank adaptation, or LoRa. The core principle here is, I think, genius in its simplicity and its effectiveness. Instead of modifying all the billions of parameters of a massive LLM during fine-tuning, which, as we've said, would be incredibly memory-intensive and computationally expensive, LoRa takes a different route. It strategically injects small, trainable matrices into specific layers of the pre-trained transformer model, most often the attention layers. Think of it like this. You're not trying to repaint the entire vast canvas of the original model. Instead, you're carefully adding tiny specialized sidecar modules, almost like detachable skill packs, into key parts of the model, primarily its attention mechanisms where a lot of the learning happens. And then only these small newly added matrices, which often represent a tiny, tiny fraction of the original model's total parameters, are actually trained or fine-tuned. The vast majority of the original model stays frozen.
Wow, so you're not retraining the whole giant thing, just these tiny targeted additions. What's the massive technical benefit of doing it that way?
The technical benefit is immense. This approach drastically reduces VRAM consumption and computational costs during the fine-tuning process. Yet, very often, it achieves performance that is comparable to full fine-tuning, where you do update all the parameters. This means you can potentially adapt a massive model, say a 70 billion parameter model, using far less hardware than would be required if you tried to update all of its parameters directly. And here's that nuance again, the one that academic papers often don't explicitly highlight, but it's crucial for practitioners: the optimal LoRa rank. Remember, that's the dimension of these small matrices, basically, how much capacity these sidecar modules have to learn. It can and often should vary. For smaller base models, maybe a 7B model, a higher LoRa rank might actually be necessary.
Okay.
Because the smaller base model inherently has less representational capacity to start with, by giving it a higher LoRa rank, you're providing more adaptation depth or expressiveness to those specialized modules. You're giving the smaller model more room to adapt and capture sufficient information from your specific data to achieve good performance. It's a really key design choice that impacts how deeply and effectively the model adapts to your task.
That's great insight. Yeah, it's not just a one-size-fits-all setting, that LoRa rank parameter. It depends on the base model, too. Okay, and then you mentioned QLORI. How does that take efficiency even further? Sounds like LoRa plus something else.
Exactly. Quantized LoRa, or QLoRa, takes the parameter efficiency of LoRa and pushes it even further by combining it with quantization. So, for example, in 4-bit QLoRa, the base model's weights themselves are loaded into memory in 4-bit precision. That means they occupy significantly less space, maybe a quarter of the space of 16-bit weights. But critically, only the small LoRa adapters, those little sidecar modules, are typically trained in a higher precision, maybe 16-bit. This combination further minimizes the overall memory footprint during training, allowing truly enormous models that would otherwise be absolutely impossible to fit onto consumer GPUs to be fine-tuned effectively. And that bits and bytes library we keep mentioning is absolutely crucial here. It provides the optimized kernels needed to handle this on-the-fly quantization and dequantization during the training process, making it all work efficiently.
Right, so you're really getting the best of both worlds there. The efficient adaptation from LoRa and the extreme memory savings from quantization, allowing you to train bigger, more powerful models on more accessible hardware. That's huge. And DPO, you flagged that as a powerful method earlier too. How does that fit into this picture of fine-tuning for like better behavior or alignment?
Indeed. Direct preference optimization, or DPO, is a really powerful and I think elegant alternative to the more traditional reinforcement learning from human feedback, or RLHF. RLHF historically has often been quite complex. It usually requires training a whole separate reward model just to score potential outputs, and then using reinforcement learning algorithms, which can be unstable, to guide the main LLM towards better outputs. DPO simplifies this process significantly. Instead of needing an explicit reward model, DPO directly optimizes the LLM's policy, its way of generating text to align with human preferences. It does this using a much simpler, more stable loss function that's derived directly from pairs of preferred and dispreferred responses that humans have labeled. This dramatically streamlines the alignment process. It makes it more stable, generally easier to implement, and more computationally efficient for achieving those desirable model behaviors like helpfulness and harmlessness. It's a very neat solution to the complex problem of making models align with what we actually want them to do.
That makes sense. A more direct route to alignment. Okay, that's a solid breakdown of the fine-tuning methods themselves and their unique advantages. Now, you also mentioned acceleration and scalability earlier when we talked about LLaMA Factory's features. What exactly are Flash Attention 2 and Deep Speed doing behind the scenes to speed things up so dramatically, especially when using multiple GPUs?
Right. These are absolutely vital components for pushing the performance envelope, especially in large-scale LLM training and fine-tuning. Let's start with Flash Attention 2. This is an incredibly optimized implementation of the attention mechanism. To really appreciate its impact, remember that in a transformer model, the attention operation is how the model weighs the importance of different words or tokens in the input sequence when it's generating an output. It decides what to focus on. It's an incredibly computationally heavy and memory-intensive part of the architecture, often forming a major bottleneck, especially with long sequences. Flash Attention 2 cleverly reorders the computations and significantly reduces redundant memory reads and writes during these attention calculations. It uses techniques like tiling to keep things in the faster GPU caches. The result: massive speedups, often 2x or even 3x faster for the attention part, and substantially lower memory usage for those critical attention operations. It's a low-level optimization, but it yields huge gains in overall training speed. Then we have Deep Speed. This is a comprehensive deep learning optimization library originally developed by Microsoft Research. LLaMA Factory leverages it primarily for enabling efficient distributed training across multiple GPUs, particularly using configurations like 0.3, which stands for Zero Redundancy Optimizer. DeepSpeed intelligently partitions various components of the training process, the model states, and the computation itself across all the available GPUs.
Okay, hold on. So it's not just running the same model copy on different GPUs with different data batches. It's intelligently splitting up the actual model itself and its associated data across them. What exactly are these model states that it partitions?
Exactly, you've nailed the key idea. It's much more sophisticated than simple data parallelism. When we talk about model states in the context of DeepSpeed 0, we're referring to three main components that consume significant memory during training. 1. Parameters. These are the actual learned weights of the model, the billions of numbers that define its knowledge and capabilities. They take up a lot of space. 2. Gradients. These are the signals calculated during the backward pass used to update those parameters. They tell the model how to adjust its weights to reduce error. For every parameter, there's a gradient, so this can also be huge. 3. Optimizer states. These are the internal variables that the optimization algorithm, like Atom or AtomW, uses to manage the parameter updates effectively, things like momentum terms. These can sometimes be even larger than the parameters themselves. Deep speed, especially with 0 stage 3, cleverly shards all three of these components, distributing them across your available GPUs. No single GPU holds the entire model or optimizer state. This allows for the training of models that would be far, far too large to fit onto a single GPU alone, and it dramatically speeds up the overall training process by efficiently distributing the workload and minimizing redundant memory usage on each device. And of course, to enable that efficient distribution and coordination, multi-GPU communication becomes absolutely paramount. Libraries like NCCL, the NVIDIA Collective Communications Library, are essential. They provide highly optimized routines for collective communication operations like all-reduce, which are needed to aggregate gradients across GPUs. And the hardware interconnects matter too. Things like NVLink, which provides high bandwidth direct links between GPUs, or modern PCIe Gen 5, provide the necessary high bandwidth, low latency pathways. These are absolutely critical for seamlessly distributing workloads and data during parallel fine-tuning. Without fast interconnects and efficient communication libraries, the GPUs would just spend most of their time waiting for data from each other, completely negating the benefits of using multiple GPUs in the first place.
Wow, okay, so it's really a combination of cutting-edge software optimizations like deep speed and flash attention, paired with powerful hardware communication links, all working together for maximum efficiency and scale. That's impressive. Finally, let's circle back one more time to 4-bit quantization. It sounds almost like magic, reducing memory so much. How specifically does it work to achieve that, and what's the actual trade-off? You mentioned it was often negligible, but is there any hit?
Right, let's clarify that. 4-bit quantization, as implemented in techniques like QLOR using bits and bytes, is truly a cornerstone of efficient fine-tuning today. It's what really democratizes access to these larger models. Fundamentally, it means that the model's numerical weights, those billions of parameters, are stored and loaded into GPU memory using only 4 bits per weight instead of the standard 16 bits for half precision FP16 or BF16 or 32 bits for full precision FP32. To put it simply, each weight uses significantly less memory, exactly 1/4 of the memory compared to 16-bit weights. The bits and bytes library provides the specific, highly optimized computational kernels needed to perform this quantization, often dynamically, and also to dequantize the weights back to a higher precision, like 16-bit, just before they're used in computations during the forward and backward passes. This allows models with tens or even hundreds of billions of parameters to be fine-tuned on GPUs with significantly less VRAM than was previously imaginable. This is a key factor, maybe the key factor, in moving powerful LLMs out of those massive exclusive data centers and onto more accessible hardware, even potentially high-end consumer GPUs in some cases.
It still sounds almost too good to be true. There's always a trade-off when you compress data like that, isn't there? What's the actual technical trade-off for 4-bit quantization? Is there a noticeable loss of quality or accuracy in the model?
There is a theoretical trade-off in numerical precision. That's unavoidable. Using only 4 bits means the exact value of each weight is represented less precisely. Think of it like storing a number with fewer decimal places available. You lose some fine-grained detail in each individual weight value. However, and this is the crucial part, numerous studies and practical applications have found that for most fine-tuning purposes, this loss of precision is often remarkably negligible in its impact on the final model's performance on downstream tasks. Researchers have developed clever techniques like using specific data types like NF4 normal float 4 and double quantization within libraries like bits and bytes to minimize the accuracy degradation. So while there's a tiny theoretical hit to the model's raw numerical accuracy at the weight level, the enormous memory savings, which might enable you to fine-tune a much larger, more capable base model in the first place, or use larger batch sizes for faster training, far outweigh this minor precision loss in the vast majority of real-world use cases. It's a very calculated and highly effective compromise that pays huge dividends in terms of accessibility and practical feasibility, allowing you to train models that would otherwise be completely out of reach for many users and organizations.
That's truly insightful. Okay, it's clear now that LLaMA Factory isn't just some simple wrapper script. It's a sophisticated, well-engineered platform that leverages some of the most advanced techniques available in LLM training and optimization, making what was once nearly impossible actually quite possible for a much wider range of people. All right, so we've gone through the how-to of LLaMA Factory and taken a really deep dive into its underlying techniques. But what about the real-world performance? Where does the rubber meet the road? How much faster or more efficient are these methods we've been discussing, really? And what kind of hardware truly makes a noticeable difference in those benchmarks? For someone maybe considering investing in hardware or cloud time, what do the numbers tell us?
This is where we truly see the practical impact of all these innovations, yeah. And let's start with the hardware, because it really sets the stage for what's possible at a high end. The NVIDIA H100 GPU is currently a real powerhouse in this domain. It's built on NVIDIA's Hopper architecture. Key specs include an impressive 80 GB of very fast HBM3 memory, and it's capable of an astounding 528 tensor TFL OPS for FP16 operations. That's half precision floating point, very common in deep learning.
Okay, 80 gigs in memory, over 500 TFL OPS, those are big numbers. But what do those specific specifications actually mean in practice? Why are they so critical for high-performance LLM fine-tuning?
Right, they're not just abstract numbers, they translate directly into capability. That high memory capacity, the 80 GB of HBM3, allows you to load much larger models directly into the GPU's memory. It also lets you use larger batch sizes during training, which can significantly accelerate the training process by processing more data in parallel per step. The sheer computational power, that 528 TFL OPS for FP16, directly translates into faster training throughput. Matrix multiplications, the core of deep learning, just happen much, much faster. And crucially, as we touched on, its advanced NVLink and PCIe Gen 5 support enable incredibly efficient multi-GPU communication. This is absolutely vital when you want to scale fine-tuning tasks across multiple cards. It prevents communication bottlenecks that would otherwise just cripple performance and negate the benefits of adding more GPUs. It's really a holistic design optimized for both speed and scale in AI workloads. Now, to understand the efficiency gains from techniques like LoRa in practice, we can look at benchmarks that directly compare full fine-tuning versus LoRa. Researchers have run experiments directly comparing the time it takes to fine-tune a model using the traditional full fine-tune approach, where every single parameter of the LLM is updated against using a LoRa-based approach, often on powerful hardware like an H100 GPU to see the difference clearly.
And the results. Does LoRa really make a significant, measurable difference in terms of the actual time it takes to train the model?
Oh, absolutely. The results consistently and quite unequivocally show that LoRa achieves substantially faster fine-tuning times. We're often talking orders of magnitude quicker than full fine-tuning for many models and tasks. This clearly highlights LoRa's immense efficiency in reducing the computational requirements. It powerfully reinforces that critical insight we discussed, the trade-off between efficiency and adaptation depth. LoRa demonstrates that you can often achieve nearly comparable performance for many tasks, but at a fraction of the time and computational cost. This makes it a highly viable and often the preferred alternative for scenarios demanding faster iteration, faster fine-tuning, especially when computational resources are limited or expensive. It really changes the game for the speed of research and development in this space.
That's a massive win for practicality and just being able to iterate and experiment more quickly.
Okay, what about scaling beyond just a single GPU? How does the performance picture change when you start adding more H100s? Say going from 2 to 4, maybe up to 8 GPUs. What happens then?
That's where scaling with multiple GPUs truly comes into play, and we observe a really fascinating interplay between GPU utilization and memory usage per GPU. When researchers analyze GPU utilization and memory usage across different numbers of H100 GPUs, for example, comparing setups with 2, 4, and 8 GPUs running the same fine-tuning task using something like DeepSpeed, the results often indicate that using 8 GPUs leads to higher average GPU utilization compared to using just 2 or 4 GPUs. Wait, so the more GPUs you add, the better they're utilized on average. As a group, that seems a bit counterintuitive. Initially, you'd think maybe coordination overhead would increase.
It does seem a bit counterintuitive, but it suggests that the communication and synchronization overheads between GPUs, relative to the computation being done, become more efficient at a larger scale, at least up to a point with these modern interconnects. The system, when properly configured with libraries like DeepSpeed, can better parallelize the task partitioning the model, the data, the gradients more effectively. This potentially reduces the amount of time individual GPUs spend idle or just waiting for data or synchronization signals, which can sometimes happen more often in smaller, less optimally balanced distributed setups. Conversely, and quite interestingly, the average memory usage per individual GPU tends to decrease as the number of GPUs increases.
Okay, that makes sense.
Yeah, this is because the overall workload, including the model parameters, the activations generated during the forward pass, the gradients computed during the backward pass, and the optimizer states is distributed across more devices. Each GPU carries a smaller fraction of the total load, reducing the memory burden on each individual card. This, in turn, allows you to train even larger models than would fit on fewer GPUs, or potentially use larger batch sizes per GPU for even more speed.
Right, so each GPU individually carries less of the memory load, letting you tackle bigger problems. But does that decrease in memory usage per GPU always mean pure, unadulterated efficiency gain? Or could there be something more subtle going on there that the high-level benchmarks might not immediately capture? For a learner wanting to dig deeper, what might they consider thinking about?
That's a very insightful question, and it definitely points towards the complexities that the source materials often imply but don't always fully detail. While this decrease in memory usage per GPU is generally a massive benefit for fitting larger models, it does raise an important question for deeper research and practical optimization. Does this also perhaps point to potential, maybe small, inefficiencies in memory allocation or load balancing at certain scales, particularly if the workload isn't perfectly divisible across the GPUs? And how might different, more advanced parallelization strategies, things like tensor parallelism, where you split individual layers, or even matrix multiplications across GPUs, or pipeline parallelism, where different layers run on different GPUs concurrently, or maybe different deep speed zero optimization levels, 0, 1, and S2, net of 3, further impact these specific metrics of utilization versus memory. These advanced strategies can sometimes squeeze out even more performance or allow for even larger models by overlapping computation and communication more effectively, really pushing the boundaries of what's possible in distributed training. It's definitely a key area for ongoing research and optimization, especially in truly large-scale industrial training environments.
That's a great thought for some to dive even deeper into the cutting-edge research side of things. Okay, finally, let's talk about data volume. How does the sheer amount of training data affect the fine-tuning time? Is it a simple linear relationship, double the data, double the time, or is it more complex than that?
It's a fairly direct and usually quite significant relationship. There was an experiment that evaluated exactly this, how increasing the number of training samples affects the fine-tuning duration, specifically on an H100 GPU, using a particular model like DeepSeek-R1 Distill LLaMA 8B. They compared two vastly different dataset sizes. One was relatively small, about 24 MB, containing roughly 52,000 samples. The other was substantially larger, weighing in at around 4 GB, containing approximately 4.2 million samples. So a big difference in scale.
And the findings? Pretty much what you'd expect. Or were there any surprises in how much longer the larger data set took?
Yeah. The findings were quite clear and pretty much what you'd expect. Larger datasets lead to substantially longer fine-tuning times. It wasn't necessarily perfectly linear, but the difference was dramatic. This clearly demonstrates that dataset volume is a primary determinant of training efficiency and, consequently, the overall computational cost of fine-tuning. It really underscores that fundamental trade-off between model performance and training cost. While larger, high-quality datasets generally lead to models that generalize better and often achieve superior performance on the target task, they inherently demand significantly more computational resources, more GPU hours, more energy, and simply more wall clock time to process. It forces practitioners to be really strategic about data curation and selection.
Right, it's that classic balancing act. Aiming for better performance often comes at a significantly higher computational price tag.
Yeah.
Are there any sort of hidden complexities or challenges that come with using really massive data sets that maybe the sources didn't cover explicitly, but that might trip up someone trying this at a very large scale?
That's a good point. The sources, while clearly highlighting the impact of dataset size on time, often don't delve deeply into the nonlinear scaling effects or the specific operational challenges encountered with truly massive datasets beyond just saying it takes longer. For instance, they might not explicitly discuss potential data loading bottlenecks that can easily emerge when you're trying to feed potentially billions or trillions of tokens to your hungry GPUs. Your expensive GPUs might actually end up sitting idle, just waiting for the data pipeline reading from disk, pre-processing to catch up. That's incredibly inefficient.
Yeah, you don't want that.
Definitely not. Or they might not cover the increasing necessity for more sophisticated data management techniques during training itself. Things like efficient data sharding, splitting the massive dataset into smaller, manageable chunks distributed across nodes, or implementing data streaming pipelines to prevent the entire training process from becoming I/O bound, where the bottleneck shifts from GPU computation speed to how fast you can read data from storage. These become absolutely critical considerations when you move from fine-tuning on millions of samples to maybe tens or hundreds of millions or even billions, which is common in large-scale pre-training or very extensive fine-tuning efforts. Getting the data logistics right can significantly impact your overall efficiency and success at that scale.
Fascinating. Yeah, so it's not just about having the massive data set, but also about being able to effectively and efficiently get that data to the model where and when it's needed during training. Lots to consider there. Wow, what an incredible deep dive we've taken today. Seriously packed with information. We began by really understanding the fundamental why behind fine-tuning these large language models. We broke down their limitations as generalists and explored the immense benefits of specialization, everything from improved accuracy and fewer hallucinations to significant potential cost savings. Then we plunged headfirst into LLaMA Factory itself, seeing how this really ingenious open source framework is truly democratizing LLM fine-tuning. We looked at its intuitive web UI, its fast model support, and those cutting-edge optimization techniques like LoRa and Keylora that make so much possible. We meticulously walked through the practical steps, setting up the environment, preparing data, configuring the run, deploying the model. And then we peered under the hood at the advanced concepts driving its efficiency. From the magic of flash attention 2 speeding up attention, to the distributed power of deep speed for scaling across GPUs. And finally, we explored those real-world performance benchmarks, highlighting the impact of powerful hardware like the H100, and digging into the clear trade-offs involved between different fine-tuning methods, efficiency, and dataset size. Our mission today was really to equip you, our listeners, with valuable, practical insights into adapting powerful AI for your specific applications, focusing squarely on the technical innovation that underpins these advancements. And we sincerely hope this deep dive has done just that.
Absolutely. And as frameworks like LLaMA Factory continue to evolve, as they continue to simplify the sophisticated process even further, enabling highly effective fine-tuning, even on, let's say, more modest compute resources than were needed just a year or two ago, it truly opens up an incredibly expansive world of possibilities for customization. So maybe a final thought to leave you with. Considering this dramatically increased accessibility of LLM adaptation and customization, what new, maybe highly specialized domains or even hyper-niche applications do you envision becoming practical and impactful through targeted LLM fine-tuning in the near future? Perhaps it's a personal writing assistant trained solely on your unique style and vocabulary, or maybe a historical expert focused entirely on a single, obscure, ancient civilization trained on all available texts. The possibilities, really driven by these relentless technical advancements making customization easier, are truly becoming limitless.